Hello, everybody. We're back. So today we're going to take a look at electric fields and adding electric field vectors together. We've been sort of circling around this for a little bit now. We've gone over how a charge creates an electric field in space. We've gone over how that can be calculated. We have also looked at how to add vectors. And today we're going to put it all together. So what we are going to do in a moment is work on this worksheet here called the direction of electric fields. I was going to walk you through the examples on the front, which are qualitative, meaning no numbers, and then 2 on the back. You have this in your packet of worksheets. If you don't, you can print one up real quick. It should be attached. However, before we do that, I thought we would take a moment. If this was in regular class, I would be leaning up against the left side of the board, and I would say, okay, let's talk about what we've done so far. And I just want to remind you, when we're looking at the electric field around a point charge, what we're really looking at is what type of force it can apply to a charge if placed in that field. So in order to calculate that, we're going to use our formula KQ over R squared. Now this is a vector. So you've got to make sure that you realize when we add these together, these are vectors. That might be the most important lesson of the day. Now, as a reminder, K is that constant 9 times 10 to the 9th, Newton meter squared per Coulomb squared. Q is charge. And just as a reminder, please don't be offended, micro and nano. Nano. What number does nano sound like? 8? No, what are you, an idiot? No, it sounds like 9. Nano is times 10 to the minus 9. Sorry, I knew you knew that. Nice job. R is going to be the distance from the center of the charge. Now, where this is all going to tie together is that it's really easy when there's only one charge. But what happens when there's 2 or 3 or 4? That's when we get to start doing our vector addition. But again, we take things in steps. So remember, what we're really looking at here is that if we were to take a test charge and bring it close to this other charge that's creating a field, if this was a positive test charge, it would experience a force away. If I moved it closer, it would experience a greater force because the electric field would be greater. Right now you're thinking, yeah, Mr. Edgar, I get it. Let's move on. Before we do, real quick, if we know what the electric field is at that point, we can utilize our relationship F equals QE to find the force. And then once we find the force, we could find the acceleration by saying the sum of the forces will cause that mass to accelerate. And that force, you got it, is going to be QE causing the mass to accelerate. All right, again, a little bit of foreshadowing. So if you could you go to that worksheet that we have, and I'm going to talk you through some of it, and we'll do some of them together. Sound good? So if I pull that up, here it is. My vision is a little blurry here, but let's talk through it. Here's where we have a classic type of physics problem. What's going to happen if we put these on a number line? What I want to do, I want you to please indicate the direction of the electric fields due to each charge on the number line below. For the sake of comparison, draw in the electric fields from the left charge on top of the line and from the right charge below the line. And this is the key. I want you to indicate with a big X in what region, left, middle, or right, the electric field is equal to 0. Okay? Now, what we're doing in this is that we are limiting our problems to being on the number line instead of in the X and Y plane. It's just going to be on the number line, making it much easier. So, positive 2Q. The Q could be anything, but it's plus 2Q. Okay? So the charge would be plus 2 relative to the charge on our right, which is plus 1. So from the plus 2 charge, we're going to have field lines that emanate away from that charge. In fact, they're going to even continue past the plus Q. The plus Q charge is going to have field lines that point away from it. Now, because I have separate pens here, come on, I'm going to do them in different colors. Yippee! Now, they're going to point away, 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 away. Now, with this visual, it becomes pretty clear where the electric field could possibly be equal to 0. Look at the left-hand side. Both vectors are in the same direction. Are they ever going to cancel out? Nope. Look in the middle. Are they pointing in opposite directions? Yeah. Somewhere in between there, that field is going to be equal to 0. Now, my computer's a little touchy, just like some of you guys, a little sensitive. It's okay. I'm going to put a big X right about here, where those two field lines have the potential to cancel out. Now, I do want to note which direction is positive. Yep, I'm going to make right positive in all these problems. Now, lesser students will get confused between the positive sign that gives direction and the positive sign on the charge. Yeah, good luck with that. To give you a visual, here I have a PHET, P-H-E-T, lined up, where I have two charges placed in space, and right now they're equal to each other. So it makes sense that the electric field is 0 in the middle. But as I move the sensor closer to the right-hand charge, it gets bigger and bigger and bigger, because it points away. I'm going to take this and make this a 3 charge versus 1. Line them up all on top of each other. And let's take our sensor. Along this line, if I start way over here, and I'm moving from left to right, ready? I'm going to move left to right. See how the electric field is always pointing to the left. It never changes direction. As I actually get closer to this point charge, it's going to reach infinity. Oh, gosh. Let's move past that point. And now it pushes away. And it's much larger because it's closer. But then as we move in between the two charges, it's going to get smaller and smaller. And at some point, reaches 0. Now, we have a charge of 3 on one side and 1 on the other. So it doesn't cancel out in the exact middle. Maybe we'll deal with that mathematically in a moment. But visually, yeah. All right, let's look at the next one. Next one. Next one. I got a plus 2Q and a minus 3Q. Let's check that out. Were those first two problems too easy for you? Yep, they were. Let's see if this trips you up. I'm going to have a plus 2, so points away, along that line. The minus 3 charge, the minus 3 charge is going to point towards, and it's a bigger charge. So the field lines are going to start off bigger at first. Now my question is, where's it going to cancel out? Now your first instinct would be, say, the middle, because the first two were in the middle. But obviously both of those field lines in the middle here are pointing to the right, so they're never going to cancel out. On the left-hand side, behind the plus 2Q, they're in opposite directions, but also behind the minus 3Q. I got to tell you, for the electric field, which is what we're dealing with right now, there's only one place on that number line where it's equal to 0. Do you know where it is? That's right. It's behind the plus 2Q. Now, if we were in class, I'd look out and I'd see the confused look on your faces. And I have to explain it this way. Look, Let's look at the place it's not, over to the right of the minus 3q. If I'm over in this position right here, okay, let's call that position P for position. It's always going to be closer to the minus 3 charge, which is always going to be bigger. So throughout this entire region, the field line from the minus 3q is going to be bigger than the field lines from the plus 2q. Let's go to the left where the real answer is. Somewhere over here, some distance r from this, that's a fat marker, some distance r, the fact that the plus 2q charge is closer will cancel out the fact that the minus 3 is farther away. Yeah. And if I wanted to write that out in words, okay, math words, I could write that as the sum of the electric field is equal to 0 at a certain point. Now, the sum of that electric field is going to be minus the electric field from 2 plus the electric field from 3 is equal to 0. Now, where did those minuses and pluses come from? Yeah, that's right. They came from the fact that if we make right the positive direction, E2 was initially pointing to the left, making it negative, where E3 is pointing to the right. Whew. All right. Moving on, last one. Actually, you know what? Let's go look at a quick sim of that. Real quick. 3. And the electric field at that point in between the two charges is always going to point to the right. If I go behind this charge at a certain point, it's going to go to 0. So, yep. But it's never going to go to 0 behind the larger charge. It's going to get smaller, but it's never going to go to 0. It's true. It's true. That's the answer. All right, this is dragging on. The last one. Skip it. Turn the page, if you would. Let's turn the page. It asks you on this, we're only going to do part A for number 1 and part B for number 2. On the number line below, each increment is equal to 1 meter. Now, in part A, it says, find the electric field strength at point P. So at point P. Now, there's 2 electric fields acting on it, correct? The charge that's on the left of plus 2 microcoulombs is going to apply a force, or it's going to have a field that points away. I'm going to call that one E1 because it's the first one and I'm counting left to right. Now, the other positive charge is going to cause an electric field pointing away from itself. Now, it's farther away, so I can draw that arrow as smaller. Now, all right, took a deep breath and the music starts. Actually, that's the bell. So, and we're back. All right. Now, this is a different problem than what I was just dealing with. Here, I just need to find the electric field strength at point P. It's going to be the vector sum of the fields caused by those 2 different charges. I'm not finding where the electric field is equal to 0. I am merely finding what is the electric field strength at that point. And we've done vector addition review where we've added 2 vectors. Ooh, one's going to the left, so we could also call that vector subtraction. But what I need to make sure I do is define which direction is positive. Now, when I find the sum of the electric fields, I am simply going to add them up as if they're just vectors. So E1 is in the positive direction. E2 is in the negative direction. So the sum of those is you just add them up. Now, the formula for electric field is going to be K Q1 over R squared minus KQ, I'll call the other one KQ, KQ2 over R2 squared. Now, mathematically, it would be elegant if I were to factor out the K. I may not do it this time. That's okay. So if I do the sum of the electric fields equals, now K is 9 times 10 to the 9th. Q1 was 2 microcoulombs, so 2 times 10 to the minus 6 divided by, well, the distance looks to me to be 3 check marks over, so 3 meters squared. Now, because the other vector is pointing to the left, it's going to be minus 9 times 10 to the 9th, 2 times 10 to the minus 6, divided by 1, 2, 3, 4, 5, 6, 7, 8, 9. Geez, it's like somebody figured out the numbers ahead of time. 9 squared. Now, could you take a moment, put your pen down, and plug it in? Now, this is where teaching on my own scares me, because I don't have somebody to check this with. But I got 1,777.777778 newtons per coulomb. Anybody else get that? Yeah, what are you going to say? Doesn't that look stupid? You'd never write that many digits. You'd never just write what's on your calculator. We got around this. And in physics, we often go with 3 significant digits in our answer so that we don't fight about it. But I have the sum of the electric field is 1,780 newtons per coulomb. And because the answer is positive, that would indicate that it's going to the right. The positive sign tells me that direction, so you don't need to hit it. Well, there's the music again. I'm back. All right, so if I zoom out on this one, all we were doing was finding the electric field at a point P, and we just added the vectors together. Check. Now, next, instead of finding the electric field again at point P, I want to find nothing to do with P, but where does the electric field equal 0? And this, mathematically, is going to be a little uglier, right? Smaller. Here we go. So if I were to look at the direction of the vectors at each region, where would the electric field cancel out? One fail-safe way to write it out is to draw in your arrows. They point away from the positive. They point towards the negative. So yes, it's going to occur behind the smaller charge. The smaller charge will be closer than the larger charge, and that'll make up and at some point cancel out the fact that it's smaller. Okay, so if that's the case, I'm going to define this distance as r. Now, up above, we just found what was the sum of the electric field. This time, we're going to find where it's equal to 0. So the sum of the electric fields is equal to 0. So my plus 2 charge is going to be pointing in the negative direction. I'm going to call that negative E2. And then the minus 3 charge is pointing which way? That's correct. It's pointing to the right. So I'm going to write that as plus E3 equals 0. So where those two are equal to each other, E2, negative E2 equals whoop, negative E3. Good. Now, how is that going to help me solve for R? Well, let's look at the relationship. For E2, it's going to be KQ2 over R2 squared equals KQ3 over R3 squared. Now, you'll notice I used 2 and 3 this time because they're not the same charge. So I can just label them as the 2 charge and the 3 charge. Yeah, that's right. Nice call, guys. Good. Many of you already crossed out the K's. Good. Now, what do we put in for our other values? Well, Q2 is going to, and I'm going to write it a certain way, Q2 is equal to 2 microcoulombs. Q3 is equal to 3 microcoulombs. Hold on. You're thinking, where's the negative sign? Is the electric field a vector or a scalar? Yeah, that's right. It's a vector. As a vector, the sign comes from the direction when we are doing this problem. So if right is positive, which is what I did during this step, the signs in my calculation actually come from which way the arrow is pointing. So I do not include the sign when I plug in the charge. If you didn't catch that, rewind it, play it again. Okay? Now, for R, what do we use? For the plus 2 charge, that distance is going to be some R squared. What do I use for the minus 3 charge distance? Well, it's going to be some distance R plus, well, let's look. If we count, it's a distance R to this charge, the plus 2. So then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the distance to this point in space is R plus 14 squared. Yeah. Okay. If we keep going. I'm thinking some of you guys right now see that the microcoulombs cancel out. Whew, thank goodness, because I don't feel like dealing with that. And my next step in math would be to cross multiply. So let's do that. All right, so here we are. Done a bunch of math. You guys are in AP Physics 2. You're seniors. Got to be able to do that. Just about, hopefully I didn't make a mistake. These are the values I have for A, B, and C. So I get it into the proper quad form, A, B, and C. And for A, I'm going to have 1. B is going to be negative 56. C is negative 392. Now, if you have R equals 62.3 meters, or R equals negative 6.3 meters. I'm laughing because this last part's brutal. Do you know which one is the correct answer? The correct answer is 62.3. Mathematically, we would end up with a positive value for R. That's going to tell me the distance it is to the left. The negative 6.3 would be the answer for if it was in the middle of those 2 points. I hope you're still with me. That was a lot to take in. It's a bit of a classic AP problem, so I have to go through. Plus, let's be honest, just doing the binomial expansion was exciting. And then using the quad form. That's how you go about finding where the electric field is equal to 0 on a number line. Whew. All right. Thanks for bearing with me. Hope you guys are good. We're going to meet back in our Zoom call, or maybe there's other notes. I don't know. Everybody good? Whew. Take a deep breath. Put that piece of paper aside.